This is my trigonometry course. Today we're going to transform the graphs of trigonometric functions. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. So we learned the graphs of the basic trigonometric functions. Be sure to get a screenshot of these functions. You must get a screenshot or take a picture with your phone, because we can't go back and forth and show you these graphs over and over and over again. We could, but that would get kind of tedious, so please take a picture of these graphs and have them right in front of you for the whole class. So I'm giving you this chance to take a picture and make sure you have these right in front of you throughout this entire class. We have the sine graph and the cosine graph, and we can call these functions even though we're letting the independent or the dependent variable be y instead of f of x. So we may refer to these graphs as functions. What you can do is actually modify the graphs. We can transform the basic graphs as we did in my intermediate algebra course. This is really just review of what we did in my intermediate algebra course when we took basic graphs and transformed them. So you can see that we have omega and b and a, and all these numbers are going to correlate with a number of transformations in the basic graphs. And this is a new Greek letter. It's called phi. You can pronounce that phi. And if a graph resembles the sine or cosine curve, and understand that the word curve is used to describe any graph, even if it's a line, you would describe any graph in the study of mathematics as a curve. If a graph has the same general shape as the sine or cosine curves, we call it a sinusoidal function or a sinusoidal graph. Now, the midline is one of the most important things when analyzing trigonometric graphs. That's just the horizontal line through the middle of the graph. So an example would be this orange dotted line here. You see how it goes through the middle of the curve. That's called the midline, and that helps us to graph the function. And the equation of that line is always going to be y equals b, this number here at the end of the equations. And we're going to talk about why that is as we go along in this class today. Again, everything that we do in this class pretty much is going to be review of the transformation part of my intermediate algebra course. But you're going to need to learn how to do this, because we're going to transform trigonometric graphs. Now, the period is the number of degrees required for a trigonometric function to complete one whole cycle. So that is the horizontal distance along the x-axis in degrees for one complete cycle. Notice that this curve goes up and down, and then it starts over again. And then it goes up and down and starts over again. And up and down and starts over again. So the distance for one complete cycle is the period. So that red part there is the orange distance is the period. So the period of the basic sine function is 360 degrees. It's the part that is the solid red. So it goes from here to here until it starts over. The period for the cosine curve is also 360 degrees before the cycle repeats. The period for the cosecant curve is also 360 degrees before it repeats. We've got an upside down hill and a right side uphill, and then it starts over. Upside down hill, right side uphill, starts over. Upside down hill, right side uphill, and continues on and on and on. The period of the secant curve is also 360 degrees. So that's very important to remember. The period of the basic curves is 360 degrees, but the period of the tangent and cotangent curves, you'll notice, is actually not 360 degrees, it's 180. So that's the distance along the x-axis before the graph repeats its shape. And the same is true for the cotangent graph. If you start at 0, you see we have one whole shape here from 0 to 180 degrees, and then it repeats. So, in order to define the period of the sine, cosine, cosecant, or secant curves, we divide 360 degrees, the normal period for the basic graphs, we divide it by omega. Now, what is omega? Omega is the coefficient of x in all of these equations. Remember, when you multiply x by a number, assuming it's a whole number, you compress the graph horizontally. So picture yourself pushing the graph inward from the right and from the left, pushing it together. So you might have a basic sine curve that looks like this. If you compress it, it might look like this. So you're pushing it inwards when you multiply by a whole number. So that's why you have to divide by omega. Remember, when you multiply, in my intermediate algebra course, we learned that when you multiply x by a number, in the corresponding graph, you divide all the x values by that number, which is the exact opposite of what you would think. The exact opposite. When you're graphing using an equation, usually whatever you do to x or y in the equation, you're going to do the opposite in the actual graph. So it's very strange. For the tangent and cotangent periods, you take 180 degrees and divide by omega, because 180 degrees is the normal period for the parent basic tangent and cotangent graphs. So we're going to learn more about this as we go through this class. But now we're just introducing terms. There's a lot of special terms in trigonometry that you need to know. You already know these concepts from intermediate algebra, but in trigonometry we have special terms. For example, the phase shift. In my intermediate algebra course, we just called it the horizontal translation. When you translate a graph, you go up, down, left, right. The phase shift in trigonometry is a horizontal translation. It might be to the right or to the left. And you find that by dividing phi by omega. So you take this phi value and divide by omega. Now, why is that? Well, we don't know. We're going to do some practice problems, and then you're going to see exactly why that value is the phase shift, the horizontal translation. One more thing that we have to learn is the amplitude. The amplitude is only defined for sinusoidal functions, the cosine and the sine function. The amplitude is the vertical distance from the midline to the highest or lowest point on a sinusoidal graph. And the amplitude just happens to be this number here. Now, these other equations, they have an a value, but that's really not defined to be amplitude. Amplitude is only defined for the sinusoidal equations and their graphs. I know that's kind of confusing. One last note, the amplitude is always going to be positive. In some cases, the coefficient of the trigonometric function is negative. The amplitude is always defined to be positive, so we always take the absolute value of that number. So it says here, for the following problems, write the equation of the midline and find the period, amplitude, and phase shift, then graph the equation. So this is all going to become much clearer as we do some practice problems. So the equation of the midline is y is equal to -1. How did I know that? Well, because this number here is always going to be the equation of the midline when you set it equal to y. Now, why is that? Well, when you put it on the other side, we now see that we're adding 1 to y. Whenever you add or subtract something from y, you move up or down. So that's going to determine the midline equation. The period is given by that equation. This is a sine curve, so we're going to take the normal period for the sine curve and divide it by omega. Now, what is omega? Omega is the orange number right there. So we're going to divide, and we get 120 degrees. That's the period. What does that mean? Well, that's the horizontal distance for one complete cycle. So that's going to be 120. It's 120 degrees. The green distance is 120 degrees. That's what that means. How are we going to use this in the problem? Well, you'll see as we go along. The phase shift, I'm going to call it PS for phase shift, is equal to phi divided by omega, and phi is negative 270 degrees. Actually, in this case, it's positive. And omega is 3, so we get 90 degrees. That is the phase shift. So we have a horizontal shift going 90 degrees to the right. The sign of this phase shift can be a little confusing, but if it's a positive, that means you're going to the right. If it's negative, that means you're going to the left. But that's the exact opposite of what we see up here. We have a negative 270, so it became a positive phase shift. Why is that? Because remember when you subtract something from x, you move to the right. It's the exact opposite of what you would think. When you subtract something from x, you move to the right. When you add something to x, you move to the left. We learned that in my intermediate algebra course. Now the amplitude is just the absolute value of a, and a is 2. So the amplitude is 2. Where did I come up with that number? That's the purple number up there. So that's where I got that. So that helps us to map out our graph. But in order to show you how this relates to the transformations that we learned in my intermediate algebra course, we're going to change the form of this function so you can make sense of all this, because so far all we've done is come up with a lot of fancy names, but we haven't really explained anything. So I'm going to change the form of this equation. I added 1 to both sides, and then I divided both sides by 2. Now I am going to factor. You could graph in this form, but what you'll find is that it's much easier to factor out that 3. If you multiply back, we get 3 times x is 3x, and 3 times negative 90 is negative 270. So I factored out the 3. It's much easier to understand the graph if we write in this form. So today we're always going to write the trigonometric equation in this form. It just makes it easier for us to understand what's happening. We could graph in this form, but we know that if you add or subtract something to or from y, you move up or down. But the problem is we're not subtracting 1 from y. We're subtracting 1 from 2 sine 3x minus 270. So we don't know what to do. We have to add 1 on the other side. We're multiplying 2, not by x, but by sine 3x minus 270. So that doesn't really tell us what to do in terms of the graph. But if we divide, we can see now we're dividing y plus 1 by 2. And we can't move 270 degrees to the right, as we learned in my intermediate algebra course, because we're not subtracting from x. We're subtracting from 3x. But now we are subtracting from x, so this is going to make it easier for us to graph. So I'm not trying to complicate things, I'm just telling you that if you want to graph, you have to have some sort of a reference to know how this really works. So now we're going to graph the sine curve, and I want you to understand very clearly that each box represents 90 degrees in this particular class. So each box is 90 degrees. That's going to be the same for every single graph. So let's graph the sine curve. We have 90 degrees, 180 degrees, negative 270, or positive 270, and then 360. That's one complete cycle. Now the graph continues forever in both directions. But I'm not going to require you to draw any more than one cycle, because it just gets very tedious. Graphing in general is very tedious, so we're not going to do that. So now you see we have y plus 1 divided by 2. It's very important that you do this in a particular order. We're always going to dilate first if our equation is in this form. So I'm going to divide y by 2. And I know what to do in that situation, because when you divide y by 2, you multiply all the x values of the corresponding graph by 2. So now we're going to get this graph. So it changes the amplitude. The amplitude was 1. And by the way, I should clarify that in the vertical direction, the boxes are always going to represent 1 unit. So I have 1 unit for each box. So the amplitude was 1, but now the amplitude is 2. So that number in front represents the amplitude, because that number went down to the denominator. That tells you what the amplitude is. That's why we call that that number the amplitude. So now I'm going to dilate again, and this is something that we didn't do in my intermediate algebra course. We're going to dilate twice in the same equation. We vertically stretched y, but we're also going to horizontally compress, we vertically stretch the graph, but we're also going to horizontally compress because we're multiplying x. Whenever you divide x or y, it's a stretch. Whenever you multiply x or y, it's a compression. If you're doing something to y, it's a vertical dilation. If you're doing something to x, it's a horizontal dilation. So what this does is it divides all the x values by 3. So if the period of this curve is 360 degrees, and we know that because that's the period of your basic sine function, then the new period is going to be 120 degrees, because you take 360, the old period, and divide by 3. This point here, that the x value of that point is going to be divided by 3, which means that you're going to end up at 120 degrees, which is somewhere around there. So the curve is going to get really, really scrunched in there tightly. So we're going to Usually the sine curve is divided up into 4 parts. So your first part there, that's the first quadrant, and then the second quadrant and the third quadrant and the fourth quadrant if you interpret this in terms of the XY axes for your reference triangles. So we're going to have to divide 120 into 4 parts. 120 divided by 4 is 30 degrees. So you're going to go up 30 degrees and then down 60 to 60 degrees. You're going to cross the x-axis at 60 degrees, and then you're going to go to the highest point at 90 degrees and then go back down to 120. Now, if you're thinking that this is kind of difficult to graph, you are correct. We could change the scale of the graph, but then it would be difficult for us to compare these graphs to see what's happening. And so there's positives and negatives to changing the scale of the graph. So let's do the final transformation. Now I'm going to add 1 to y. So that moves the graph down 1 unit. And I'm also going to subtract 90 from x. So that moves the graph to the right 90 degrees. So we take this graph here and we're going to move it down. So I'm going to draw the midline. That's called the midline. That helps us graph. And I'm going to move the entire graph 1 box to the right, because each box horizontally represents 90 degrees. So I'm going to move over, but I'm going to start on the midline because we're moving the entire graph down. So I'm going to go up 30 degrees and back down 60, and then 90, and then 120. Is that kind of tedious to have to graph that? Yes. But you're going to do it anyway, because sometimes in math you just have to draw a tedious graph. So we use the transformation method to graph this complicated equation. We use steps. First we stretched vertically, then we compressed horizontally, and then we translated. And the period, the horizontal distance for one complete cycle is 120. That's what we found down here. We start at 90 degrees, and then we go out 120. That's the horizontal distance for one complete cycle. The phase shift is 90 degrees. What that means is we move the entire graph to the right 90 degrees. And the amplitude is the purple 2. The amplitude is the purple 2. That's how high the hills are from the midline. So that's 2 units, as you can see there. And we found the midline is y is equal to -1. The midline is this line here. The equation is y is equal to -1. So we're using all kinds of different things that we learned in intermediate algebra to graph these equations. So now let's move a little quicker. The equation of the midline is y is equal to 2. Where did I get that? I got it from here. The period is always equal to 360 degrees over omega, unless you're finding the period of the tangent or cotangent turn graph, then it's 180 over omega. So omega is 2, and we have 180 degrees. Where did I get omega? I got it from there. That's always omega. The coefficient of x is always omega. The phase shift, which I'm going to call PS, is equal to phi divided by omega, and phi is negative 360 degrees. I know that's very confusing. It's very confusing that it's negative, because it's not negative in it's not negative in the actual equation. It's positive 360 degrees, right? But again, if in our general equation we're subtracting phi, then phi has to be negative in order for this to turn to a positive. It's very confusing. So we have negative 180 degrees. That is the phase shift. That means we're going to move to the left 180 degrees. Textbooks will write that in different ways depending on who's writing the textbook. The absolute value of the amplitude is 3. So that is the amplitude, and I got that number from there. So now we're going to actually graph this equation, but again, we're not adding or subtracting 2 from y, we're not multiplying x by 3, and we're not adding 360 to 2x. So it's very difficult to graph this, but if we subtract 2 from y, and then we divide both sides by 3, and then factor out 2 from inside the sine function, then it makes it much easier for us to graph that equation. So we're changing the form of that equation so we can graph it more easily. So now let's write the parent sine function. So that is the parent sine function. And again, every box to the right is 90 degrees. That's 90, 180, 270, and 360. But for the vertical, we always have 1, 2, 3, and so on and so forth. So the scales are different depending on if it's horizontal or vertical, the vertical direction. So now, as usual, we're going to dilate. We're going to divide y by 3, and that's going to multiply all the y values by 3. So we go up to 3, and back down to the x-axis, and then down to negative 3, and then back up to the x-axis. So that's why this number is the amplitude. Remember, that number is the coefficient of this trigonometric function. That's the amplitude. When you put it on the other side, it actually stretches the graph vertically. That's why we call that the amplitude. So now we're going to dilate again, but now we're going to do a horizontal compression. So that means we're going to change the period of the function in the graph. So if we're multiplying x by 2, then that means we have to divide all the x values by 2. So if the period of this previous graph is 360, then the new period is going to be 180 degrees. So instead of reaching the maximum height at 90 degrees, we're going to reach the maximum height at 45 degrees, and then cross at 90, and then reach the minimum depth at 135 degrees, and then we're going to go back to the x-axis at 180 degrees. So you can see that that vertically, or actually horizontally, compressed the graph. So now we're going to subtract 2 from y, and I'm going to add 180 degrees to x. Sorry, that's kind of scrunched in there. So if you subtract 2 from y, you move the graph up 2 units. So I'm going to draw the midline, which will help us. It's a reference for us. And if you add 180 degrees to x, that means you move the entire graph to the left 180 degrees. So that's 2 boxes to the left. So now our graph, it starts from the midline because we moved up 2 units. So now we're going to go up to 45. The horizontal movement is 45 degrees, and then 90 degrees, and then that'll be 135, the total movement, and then 180. So we move the graph up 2 units and to the left 2 units because we added 180 degrees. Again, each box is 90 degrees when you're dealing with the horizontal movement. Okay, so this is a little tedious, but we're using the transformation method because it shows you a general principle that will be used in every graph that you draw in the XY rectangular coordinate system. Whenever you're graphing coordinates in the XY system, those are called rectangular coordinates. So now it's time for you to try. Go ahead and get a picture of these 2 pages here, and get a picture of these 2 pages. Please be sure to get those pictures on your phone. And now it's time for you to try. So go and attempt number 3. When you come back, we'll do it together. Okay, we're back. The midline is y equals 3. The period is 360 divided by omega. Omega is 2. Where did I get that 2 value? It came from there. And that number came from there. And so we have 180 degrees. That is the period. One complete cycle is 180 degrees along the x-axis. The phase shift, which I call PS, is equal to phi divided by omega. Phi is 90 degrees. It should be positive. And omega is 2. So we have 45 degrees. That means we're shifting to the right, which makes sense because we're subtracting from 2x. If you subtract from 2x, you're going to move to the right. If you add to 2x, you're going to move to the left. Exact opposite of what you would think. Remember, whenever you graph, the exact opposite of what's happening in the equation is what's going to happen on the actual graph of the equation when you're using the method of transformations. So the amplitude is the absolute value of 4, which is 4. And we got that from up there. And the phase shift, well, phi came from there. Okay, so now we want to graph the equation, and you can use all that information to graph the equation if you want, but it's more important to use the knowledge that we learned in my intermediate algebra course, because that's information that applies to all graphs, and you need to understand how these trigonometric graphs are changing in relation to any other graph in the XY coordinate system. So now we're going to factor the 2 out, and we get x minus 45 degrees. So we can see that the phase shift is 45 degrees because we're subtracting 45 from x. Okay, so we're dealing with the sine curve, so let's draw the parent function for sine. It looks like that. Something like that. It doesn't have to be a perfect curve. This is not an art class, so don't worry about creating a perfect curve. It just needs to go through the right points. And then we're going to vertically stretch as usual. So y divided by 4 is equal to sine x. So that's going to stretch 4 units. So I'm going to go all the way up to the very top, cross the x-axis, all the way to the very bottom, and hit the x-axis again. So then we're going to horizontally compress. So we have y over 4 is equal to sine 2x, and it divides all the x values by 2. Now this x value here is 360 degrees, the x value at that point. So we're going to reduce the size of that curve. We're going to cut it in half, so now the new period is only 180 degrees. The normal period for the sine curve is 360. If you multiply x by 2, then it reduces to 180. So it's half of what it was. And now we're going to subtract 3 from y. So now we're going to replace x with x minus 45. Whenever you subtract 45 from x, you move the graph 45 units to the right. And we're subtracting 3 from y, so you're going to move up 3 units. So we moved up 3 units, and we're going to move to the right. Normally we start here, but we're going to start 45 units to the right. So we're going to go up 45 degrees, and then down 90 degrees, and then all the way down to 135, and then all the way back up to the midline. So that is the graph. So if you got that right, excellent. Go ahead and try number 4, and when you come back, we'll do it together. Alright, we're back. So the midline is -2. I got that from there. That's the equation of the midline. The period is the normal period of the basic sine graph divided by omega. Omega is 3, so we have 120 degrees. Where did I get that? I got omega from there. The phase shift, which I'm going to call PS, is equal to phi divided by omega. Phi is -360, so it's the opposite sign, divided by 3, and again 3 came from there. So we have -120 degrees. So that means we're moving to the left. I know the signs can be pretty confusing regarding this, but it's just all based on how the general form is defined. The amplitude is the absolute value of 2, which is 2. So that is the amplitude. We got that number from there. So now we're going to graph using transformations. I'm going to add 2 to both sides of the equation. Then I'm going to divide both sides by 2. Then I'm going to factor out 3, and we see that the phase shift is 120. So the parent function is y is equal to sine x. I'm going to draw that curve. Now we're only drawing one cycle, so the cycles continue forever and to the left and to the right. You're only required to draw one cycle in my courses. So now we're going to divide y by 2, and that's going to multiply all the y values by 2. Again, just drawing one cycle. Then we're going to multiply x by 3. That's going to reduce the period of the graph by 3. So if we divide 360 by 3, we get 120. That is the period. Whoops. Period is up there. So 120 degrees. So we have to divide that period into 4 parts. Remember, this is the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. You always divide these curves into 4 parts, unless you're dealing with cotangent or tangent. Then you could divide it into 2 parts. So if you divide 120 into 4 parts, each part would be 30 degrees. So we're going to go up 30 degrees and then back down to 60, and then 90, and then 120. So I know that that's hard to graph, but this is kind of a tedious subject to have to graph all this. So now we're going to add 2 to y, and we're going to add 120 to x. So what that does is it moves the graph down 2 units. So we're going to draw what we call the midline, and we're going to move to the left 120 units. So we're going to start over here, and again we're going to go 30 degrees, then another 30 degrees, then another 30 degrees, and then we get to the origin. Let's try to make sure that it goes, whoops, I forgot to move down. We have to move all the way down, so we're going to start down here. But we're going to move 120 degrees to the left. So that would be 30, another 30, another 30, and there we go. So again, I know that this is hard to graph, but again, graphing this stuff can be pretty tedious, so just try your best. So if you got those right, excellent. Good job. Let's go on to number 5. Now we're moving to the cosine curve. Okay, so if you got those right, good job. So now we're going to go to the cosine function, and instead of multiplying x, we're going to divide x, and we also have a negative coefficient. So let's see what happens here. The midline is going to be y is equal to 3. As usual, we got that number from there. The period is the normal period divided by omega, and omega in this case is going to be a fraction. Now you see this green x over 2. You can write that as 1/2 x. It's still the coefficient. So we're going to take that green coefficient and we're going to throw it down here. So we get 1/2 in the denominator. And remember, when you have a complex fraction, you can treat the fraction line as a division operation. So we have 360 divided by 1/2, which is equal to 360 times 2/1, which is equal to 720 degrees. That's the period. So you can see that when we're dividing x by 2, because multiplying x by 1/2 is the same thing as dividing x by 2, very important to understand that. When you divide x by 2, you actually multiply all the x values on the corresponding graph, so that'll give you a period that's double what it normally is. The phase shift is phi over omega, and phi is 180 degrees. It's positive 180. And omega, of course, is that coefficient of x. And if we do the same math, we end up with 360 degrees. And the amplitude is the absolute value of that coefficient a, so the absolute value of -4, which is 4. So we got that -4 from up here. So let's take that equation and change the form so we can graph it a little easier. So I subtracted 3 from both sides, and I'm going to divide both sides of the equation by -4. And I'm going to change the form of the left side of the equation a little bit. I'm going to take this negative and I'm going to put it up here, just so it's easier for us to understand what's going on. And I'm going to choose not to distribute that negative. I'm also going to factor out 1/2. And this is something different. If you factor out 1/2, this number should get bigger. It should be multiplied by 2. I know that's kind of strange, but when you factor out a fraction, it does the opposite of factoring out the corresponding whole number. If we factored out 2, this number would become -90. But we're not factoring out 2, we're factoring out 1/2. So it actually jumps, it doubles in size to 360. That's very confusing. So just be aware that in this case, when you factor out a fraction, it's going to make this number bigger. Now, if you want to know why that's true, just multiply back with the distribution rule. 1/2 times x is x over 2. And 1/2 times -360 is -180 degrees. So again, I know that's very confusing, but that's just a math trick that we had to learn. So the cosine curve looks like the following. It's the same as the sine curve. The only difference is it's shifted 90 degrees to the left. So that is y is equal to cosine x. So now we're going to do 2 dilations at the same time. I know this is kind of a lot to take in, but we're actually going to do 2 dilations at the same time because we don't have enough room. We only have 4 of these graphs. So we're going to do 2 transformations at the same time, a vertical stretch and a horizontal stretch. They're stretches because we're dividing in both cases. Before we were multiplying x, so it was a compression. This is still a stretch. We're doing stretches vertically in the other problems also. So now let's graph that. So it's going to stretch vertically by a factor of 4, and the new period is going to be 720. So the old period is 1, 2, 3, 4. That's 360. The new period is going to be twice as long, so it's going to go all the way out to here. So we're going to go all the way up here to the very top, because we have to stretch by a factor of 4. And if the period is 720, then our graph is going to cross there, which is a fourth of the way to 720. It's going to go all the way to there and all the way back up. So we did two dilations at the same time. We stretched horizontally, and if we stretch horizontally, what that means is that we're pulling this way and we're pulling this way, so we're stretching it. And we also pulled up this way and we pulled down this way. That was the vertical stretch. So the horizontal stretch, that's x over 2, and the vertical stretch, that's x over 4. So now we're going to reflect. This is the first time that we are going to reflect. I'm going to write a negative on y. So the only difference with this graph is that we're writing a negative on y. So what that's going to do is reflect across the x-axis. Again, remember, it's the exact opposite of what you would think. You write a negative on the y, and you reflect across the x-axis. So we have the same graph. We're just flipping it. So now our graph looks like this. So there you go. So when you reflect across the y-axis, you take some point, maybe this point up here, and then you figure out the distance from that point to the x-axis, and then you go that same distance across the other side, and that's your corresponding point. You do that for every point, and it just flips it over the x-axis. So now we're ready to translate. I'm going to replace y with y minus 3. I'm going to replace x with x minus 360. So let's see if we can find some more room here. Sorry, we're kind of scrunched in there, but that is going to be the final transformation. So what this means is we're going to move 3 units up and 360 degrees to the right. So we're going to start from this graph, move 3 units up. So now I'm going to draw my midline. This is where the midline comes in handy. And we're going to move 360 degrees to the right. So 1, 2, 3, 4. That's 360. So let's mark some points here. So our graph should look like, actually that's going to need to move, those dots are going to need to move down a little bit. So our graph should look like this. The shape is going to change a little bit because notice we changed the scale of the graph. We had to do that because we didn't have a lot of room. Now again, the graph continues forever in both directions. We're just writing one cycle of the graph so you can kind of get an idea of where the graph is going. If you draw all the cycles in the window, then it makes it difficult to see what happened to the graph. So there you go. Alright, I want you to try number 6. And when you come back, we'll do it together. Okay, we're back. So the equation of the midline is y is equal to 1. I got that from there. The period is 360 degrees over omega. Omega is 1/3. So I got that from there. So that's 360 degrees divided by 1/3, which is a pretty big number. 3 times 360, because the divisor flips, and our new period is 1080 degrees. The phase shift is equal to phi divided by omega, and phi is -45. Again, I know that's confusing, that it's the opposite sign, but that's just the way phi is defined. And so now we're going to multiply by 3, and we get -135 degrees. Dividing by 1/3 is the same thing as multiplying by 3. The amplitude is the absolute value of a, which is the coefficient of the trigonometric function. So that's the absolute value of -3, which is 3. So we got that number from there. Okay, if you got those right, good job. So now we're going to subtract 1 from both sides. And then we're going to divide both sides by -3. And on the next step, I'm going to do two things. I'm going to take that negative in the denominator and I'm going to put it up in the numerator just so it's easier for us to see what's happening with the corresponding transformation. And I'm going to factor out 1/3 from inside the cosine function, and this is the part where it gets a little weird. This number should get bigger. It should be 3 times 45, which is 135 degrees. I know that's very strange that it gets bigger. But if you want to see why that works, multiply 1/3 by x, you get x/3. Multiply 1/3 by 1/30 or 135 and you get 45. So we're ready to graph now that we've got the equation in that form. So the parent function looks like this. You don't have to draw it perfectly, but it should look like a cosine curve and should go through the right points. Now we're going to do 2 dilations at once. We're going to divide y by 3, and we're going to multiply x by 1/3, and we can write that as x/3. So remember, when you divide x or y in an equation, it's going to be a stretch. So we're going to stretch it vertically and horizontally. So we're going to pull it up 3 units and down 3 units, and we're going to pull it to the side 3 units. It's got a period of 1080, so 1, 2, 3, 4, that's 360. 1, 2, 3, 4, that's 720. 1, 2, 3, 4, that's 1080. So it's going to go all the way over to the side there. So we're stretching it out. We're stretching it this way, and we're going to stretch it up, and we're going to stretch it down. So 3 units up, and let's divide this period into 4 parts. So those are the markers if you divide it up into 4 equal parts. So here we go. Here's our cosine curve. So we stretched it this way, and we stretched it this way. Now, we didn't draw any points over here, so technically it didn't get stretched that way because there's no points over there. But all these points, they get stretched that way. Okay, so now it's time to reflect. So I'm going to replace y with negative y. And that reflects across the x-axis. So your graph is going to look something like this. And it looks like I'm going to have to move the graph over a little bit. And there you go. Okay, so sorry about that if the graph was off there. Then we're going to translate. We're going to move the graph up 1. So I'm going to draw my midline. So subtracting 1 from y. And I'm going to add 135 to x. Whenever you add anything to x, you move the graph to the left, the corresponding graph to the left, or the previous graph. Okay, so we moved up 1. So now instead of starting at -3, we're going to start at -2. But we have to move 135 degrees to the left. So that's going to be approximately there. And so we're going to have a point there, and a point there, and a point there, and a point, looks like that's, we got to move that over a little bit, and there, so we can draw a curve now. So we had to start at 135, or -135, so we go 90, and then 135 is right in the middle. So in order to graph this, we go from the middle, we go 1 unit, 2 unit, 3 units to get the next point, 1 unit, 2 unit, 3 units to get to the next point, 1 unit, 2 unit, 3 units to get to the next point, and 1 unit, 2 unit, 3 units to get to the last point there. I know that's kind of confusing, but sometimes this stuff can get a little tedious. So if you got that right, excellent. Good job. Okay, so we have about 4 more problems to do today. Now we're switching to the cosecant curve and the secant curve. So the midline is the same number there. The period is again 360 degrees. That's a normal period for cosecant, cosine, sine, and secant. And omega is 2, so we have a period that's 180 degrees. And the phase shift is equal to phi divided by omega, and phi is negative 180 degrees. I know that's confusing, but it's actually the opposite sign based on the general form that we defined. And so I got that phi from there. And we have negative 90 degrees is the phase shift. Now notice that there's no amplitude. They're not asking for the amplitude because with these curves there is no amplitude. The amplitude value only applies to the sine and the cosine curves. So now I'm going to subtract 1 from both sides of the equation. Divide both sides of the equation by 2. And we do not have a reflection in this particular problem because this number is not negative. So now I'm going to factor out 2 from inside the function, and now the number actually gets smaller because you're factoring out a whole number. Now the cosecant curve, go ahead and get a screenshot of these if you haven't already gotten one. You're going to want to look at that cosecant curve at the upper right. The way that we can help ourselves draw this is by first drawing the sine curve. So that's the sine curve, and everywhere where the sine curve crosses the x-axis, you're going to have a vertical asymptote. So you have a vertical asymptote on the y-axis also. And the cosecant curve is very simply a curve that follows those asymptotes, and it goes down and it hits the top of that sine curve, and it comes from the other direction and hits the bottom valley of that other part of the sine curve, and that's it. So now we can erase the sine curve because that's not part of our graph. So that is the cosecant curve. Those asymptotes help us to graph it. So that is y is equal to cosecant x. So now we're going to divide y by 2, and that multiplies all the y values by 2. So that's not going to affect the location of the asymptotes. So when you multiply by 2, instead of the curve coming down to 1, y equals 1, it's only going to come down to y equals -2, or just +2, and -2 down here. So those u's got pulled upwards and they got pulled downwards. They got pulled upwards and they got pulled downwards. So again, we multiplied all y values by 2. So now we're going to take that previous graph and we're going to multiply x by 2. So that's a horizontal compression. So instead of the period being 360, which is what it usually is, each box is 90 degrees, so we have a total of 360 degrees before the cycle repeats. And we start getting other u's. In this case, we have a 180 degree period because you divide every x value by 2. So the new period is going to be 180. So we're going to have an asymptote on the y-axis. That doesn't change because it's on the y-axis. But this asymptote is at x equals 2, so now it goes to x equals 1. This asymptote is at x equals 4, so now it goes to x equals 2. So our graph is really getting scrunched in there. It's getting compressed. So now our graph is going to look something like this. It's getting really scrunched in there. You see that? And you might be thinking, well, I can barely see it. Well, that's okay, as long as you're graphing it correctly. We could blow this up a little bit, but the problem is you can't really compare it to these other graphs if it's blown up. Now at least you can see how things are changing. So there's positives and negatives to trying to adjust the scale. So now we're going to subtract 1 from y, and we're going to add 90 degrees to x. So that moves the graph up 1. So I'm going to draw the midline that helps us graph. And everything in the graph is going to move 90 degrees to the left. So the asymptote that was on the y-axis is now at x equals negative 90. And the asymptote that was at x equals 90 is now on the y-axis. And the asymptote that was at x equals 180 degrees is now at x equals 90 degrees. So everything got shifted to the left. And again, remember, everything got moved up 1 unit also. So now we have a graph that looks like this. I know it's kind of hard to see, but I'm not making you graph every single cycle in the window. That would be pretty tedious. Just one cycle. So there you go. Again, I know it's hard to see, but if you adjust the scale, it's going to add some difficulty. Okay, try number 8. And you want to get a picture of that secant curve. I'm going to give you one more chance to take a picture of these curves. You need this secant curve. What you want to do is draw the cosine curve. And then the secant curve is going to be on the tops and the bottom. It's going to intersect with the top of the hills of the cosine curve and the bottom part of the valleys of the cosine curve. And wherever the cosine curve crosses the x-axis, you're going to have an asymptote. So go ahead and try this problem. If you get stuck, that's okay. But try number 8. When you come back, we'll do it together. Okay, we're back. So the equation of the midline is y equals negative 1. And of course that came from there. The period is the normal period of the cosine, sine, cosecant, or secant function divided by omega. Omega changes the period. Omega is 3. How do I know it's 3? Well, that number came from there. So the new period is 120 degrees. The phase shift is equal to phi divided by omega. And phi is this number here, 270. And that's going to be negative 270 degrees over our omega value. So that's going to be negative 90 degrees. So that means we're shifting to the left. And notice that there's no amplitude. We don't need the amplitude because there's no such thing as amplitude for these functions. Add 1 to both sides of the equation to help us graph. Divide both sides by 2. Again, this is all to help us graph. It's easier to see how to graph this using transformations if we change the form of the equation. We're going to factor out 3. And there we go. So let's draw the parent secant function. First, we're going to draw the cosine function. And wherever the cosine function crosses the x-axis, we're going to draw asymptotes. And secant is going to be, actually I should keep that cosine curve. Secant is coming down and, or it's coming up and hitting that top part, and we have secant, half secant curve there and half of secant curve there. So I know it's kind of tedious to have to draw half of the curve. but the other half will go out this way, just so you know. And we'd have more asymptotes here and here if we wanted to draw more cycles. So now we're going to divide secant by 2. So that's going to move everything up. And by the way, let's erase that cosine curve now. That's not part of our graph. So that's going to move everything up. And it's going to move this down. And the asymptotes are not going to change their positions. And I'm going to erase that. We're just going to draw one cycle there. You don't have to draw the dotted part. Okay, so now things are getting kind of scrunched in here, so we're now going to compress horizontally. So the normal period is 360 degrees, but now the normal period is going to be so the normal period is 360 degrees for the basic secant function, but now it's going to be 100. Actually, it's going to be, what do we find? 120 degrees. So things are going to get really scrunched in. So we're going to divide the asymptote numbers by 3. So this is x equals 90. We're going to divide by 3, and we get 30 degrees is a location of that first asymptote. I know that's kind of tedious, but sometimes these graphs can get tedious. So the equation of this asymptote over here is x is equal to 270 degrees. So divide by 3 and you get 90. So that asymptote would be there. We're dividing all the x values by 3. So now the graph looks like this at the bottom, and like this at the top. And over here it looks like that. So again, I know that's kind of hard to graph, but just try your best. Okay, so now we're going to add 1 to y, and we're going to add 90 to x. So that means we're going to move the entire graph down 1 unit. So I'm going to draw the midline, and we're going to move everything over 90 degrees to the left. So now we have, maybe I should move this y-axis over a little bit. So moving over everything to the left 90 degrees. The first asymptote is at x equals 30 degrees, so if you move it over, it'll be at negative 60 degrees. And the other asymptote, if you move it 90, it'll go right on top of the y-axis. And we're moving down 1 unit, so the bottom part is going to be all the way down there. And the other part is going to be like this. So again, I know this is hard to graph, but just try your best. These graphs can get pretty tedious. Okay, so there you go. If you got that right, good job. Okay, on to number 9. Now we're going to move on to the tangent and cotangent curves. So the midline is y equals -2. The period is going to be different now because we're dealing with the cotangent and tangent curves. So it's 180 divided by omega, not 360. So omega is 1/3 in this case. I got that from here. So it divided by 1/3, that's the same as multiplying by 3. And then we get 540 degrees for the period. The phase shift is equal to phi over omega. Phi is positive 90. I know that's confusing, but it is positive. Positive 90 over omega, which is 1/3. So dividing by 1/3 is the same as multiplying by 3, so that's 270. So the phase shift is positive 270. So to help us graph, I'm going to change the form of this equation. Looks like we don't have a vertical shift because there's no coefficient for cotangent on this one. So then I'm going to factor out 1/3 inside the cotangent function. Okay, so if we look at the cotangent graph, if you haven't got a picture of that, go ahead and get a picture. We have asymptotes on the y-axis in multiples of 180. So I'm going to draw the asymptotes, and we have one at 180. And again, we're just going to draw one cycle. So one cycle is 180 degrees. That's all we need. But these keep going on and on and on. Not quite like that, but you get the point. In both directions, they just keep going on and on and on. So that is y is equal to cotangent x. So now I'm going to replace x with x over 3. So this increases the period by a factor of 3. We're going to multiply all x values by 3. So this asymptote is at 180 degrees. Multiply it by 3, and we get 540. So 1, 2, 1, 2, 1, 2, 1, 2. So the new asymptote is there, and the other asymptote doesn't change because it's on the y-axis. And now we can draw the graph. So obviously it's going to cross there, and it's going to look something like that. Okay, so the asymptotes help us to graph. So now we're going to add 2 to y, and I'm going to replace x with x minus 270. And so we're going to move the entire graph 270 degrees to the right. And we're going to move it up, or actually we're going to move it down 2 units. So the asymptotes are going to move 270 degrees, 1, 2, 3. and this asymptote is 6 from the y-axis, so we're going to go 6, 1, 2, 3, 4, 5, 6 out that way. So the other asymptote is right on the end here. So it was 6 out, and now it's 9 away from the y-axis. And now we're ready to graph. So the graph looks something like that. Okay, so go ahead and try number 10. You can use number 9 to help you, and when you come back, we'll do it together. Alright, we're back. So the midline equation is y is equal to 2. And I got that from there. The period is 180 divided by omega, not 360 divided by omega. Because the normal period for the cotangent and tangent curves is 180 degrees. It's not 360. So then we get 360 degrees for the new period. It's usually 180. Now it's 360. Phase shift is phi over omega, and phi is 90 degrees. And omega again is 1/2. So 90 degrees over 1/2. And the phase shift is 180 degrees. So now I'm going to change the form of the equation to make it easier to graph. So I subtracted 2 from both sides, and I'm going to factor 1/2 from inside the function. So now we're ready to graph. So the parent function is the tangent function, and if you look at your tangent graph, there's asymptotes at 90 degrees and 270 degrees, and the graph looks like this, and it continues off, and the other half of the graph is going down like so. So now we're going to dilate. We're going to stretch horizontally. Remember, 1/2 x is the same thing as x over 2. There's a lot of different ways you can write that. So when we divide x by 2, we multiply all the x values by 2. So this asymptote is at x equals 1, so it goes to x equals 2. Now there's no x values on the actual asymptote, but the asymptote still moves the same way the graph does. So this next asymptote is at x equals, did I say 1? I meant 90 degrees, so it goes from 90 to 180. And this one is at 270. So multiply that by 2 and you get 540. So 90, 180, 270, 360, 450, 540. And so let's draw our graph. Again, all the x values are just multiplied by 2. And now we're going to translate. So we're going to subtract 2 from y. That's going to move the graph up 2 units. And we're going to subtract 180 degrees from x. So the midline is now going to be up here because we subtracted 2 from y. So remember, it's the exact opposite of what you'd think. If you subtract 2 from y, you move the graph up. And the asymptotes are going to move over 180 degrees. So this asymptote is at 180. It's going to go to 360. We can't really see the other asymptote. Kind of went off the window, but that's okay. So we have a graph going up like so, and the other part of the graph is going down like so. So we got that one right. Good job. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1. And screenshot number 2. And screenshot number 3. And number 4. And number 5. And number 6. Number 7. And don't go before you get the homework. Here's the first page of the homework. And the second page, or third and fourth pages, and fifth and sixth pages, and the last page, but don't go before you get the answers. Here's screenshot number 1 of the answers, and screenshot number 2. So remember, if you don't do that homework, you're not going to gain the fluency that you need to learn the material in this course. So get that homework done completely and correctly, and I'll look forward to seeing you in the next class.